I hope we can start now.
Yes, Prof.
Yeah. Can you see my slides?
Yes.
Yeah. In the last online makeup class, can somebody start recording the class? Did anyone start? Please, somebody start recording the class. Can you hear me?
Yes, we can hear you.
Yeah, can somebody start recording the class so that if somebody is absent or if you want to revise, you can use that recording. What happened? Nobody is able to record. Let me start.
Someone has started.
Okay. Sawa. So we are looking at the application part of the rheology. Before going to the application part of the rheology, let us see some other terms that are related with the rheology and viscosity. The first term is called as fluidity. Fluidity is inverse to viscosity. So viscosity increases the resistance to flow. Fluidity increases the ability of the fluid to flow. So that is the difference between the fluidity and viscosity. So both of them are inversely proportional to each other. Am I clear what do you mean by fluidity?
Yes.
Fluidity is represented by using the symbol phi, which is given as the formula 1 over viscosity. So this is called as phi. So this is called as fluidity. The second term is kinematic viscosity, which indicates viscosity of the fluid divided by density of the fluid. Viscosity when compared with the density of the fluid, then that is called as kinematic viscosity. And there is another term called as relative viscosity, which indicates viscosity of a reference is compared with the viscosity of the sample. Sorry, sample comes on the top and reference comes in the bottom. This is called as sample over the viscosity of the reference. So this is called as relative viscosity. Am I clear?
Yes.
Yes.
The units for fluidity are Stokes. The units for viscosity are kinematic viscosity. Gram per centimeter per second are the unit for the viscosity. And what are the units for the density? Grams per centimeter cube. Isn't it?
Yes.
So now when you cancel the terms, centimeter second multiplied by centimeter cube over gram, these two get cancelled. So now we have centimeter square over second. So these are the terms for the kinematic viscosity. The units for the kinematic viscosity. For relative viscosity, we don't have any units because on the top and the bottom we have the same terms viscosity. So there are no units for the relative viscosity. So these are the other three terms which are related with the viscosity: fluidity, kinematic viscosity, and relative viscosity. We already know that the other terms: shear stress, rate of shear, thixotropy, and another addition is negative thixotropy or rheopexy. Can anyone tell me what do you mean by thixotropy? Did you remember what do you mean by thixotropy?
Yes.
What do you mean by thixotropy?
Something
It is
shear
the
timing.
regaining of
Something like
viscosity after shear stress is removed.
Yeah, it is decrease in the viscosity when the shear stress is removed, isn't it? And negative thixotropy, it is increase in viscosity when shear stress is removed, otherwise called as rheopexy. Opposite of thixotropy. In thixotropy, there is a drop in viscosity the moment you stop shearing. But in negative thixotropy, there will be increase in viscosity the moment we stop shearing. So it is also called as rheopexy. So we can see these type of behaviors in dilatant systems or shear thickening systems, like in magnesium magma, or you can take the example of the paste. So where the solid content is more, we can see the behavior of negative thixotropy. Am I clear about all these terms that are related with the rheology?
You are clear, Prof, but last class when we were discussing the thixotrophy, you stated that is the process of regaining the viscosity. And now you are telling that it's the process of decreasing the viscosity. So which is which?
No. Thixotropy is a decrease in viscosity, not a regaining viscosity. We expect the system to, like when we shear, what happens in shear thinning systems is they lose viscosity, they decrease in viscosity, right? The moment you remove the shear, the system need to regain its viscosity back to original viscosity, but it doesn't do that. In the process of regaining viscosity, there will be a loss in viscosity. Am I clear now?
Yes.
The one who asked me the question, is it clear to you?
Yes, it's now clear, Prof.
Yeah, it is not regaining viscosity. In the process of regaining viscosity, the system will not get back to original viscosity. There will be slight drop in viscosity because the system will not be able to establish all the bonds that were lost during the shearing. So it will take some time and it will try to establish, but it may not be like the original. So there is a slight drop in viscosity, which is called as thixotropy. Are we clear about the fluidity, kinematic viscosity, relative viscosity, shear stress, rate of shear, thixotropy, and rheopexy?
Yes.
Yes.
Very good. So let us start with the applications of rheology. So in applications of rheology, this rheology is going to be used as identification parameter. So as we discussed in our last class, so this is going to act as one of the identification parameter for the materials. So like for an example, so we can have the materials, like when we take water, it will have its own viscosity. Or when we take alcohol, it will have its own viscosity. So the values are, like for water, the viscosity is around 1.002 CPS. For plasma, the viscosity is 1.5 CPS. For ethanol, it is around 1.19 CPS. And for glycerin, it is around 36.7 CPS. So which is near to 35 to 40. So these are all the different materials and their corresponding viscosity. So by using these values and by measuring the viscosity of the fluid, we can identify the material that was given, and we can it is not only the confirmation test, but you need to also perform other tests to confirm the material is so and so. But viscosity can also be used as one of the identification parameter. And also viscosity is used as one of the quality control parameter. So when we want to confirm the stability of certain dosage form like solution, or maybe the syrup, or maybe the suspension, or maybe the emulsion. So by measuring the viscosity, so we can confirm the quality of the products. So just for an example, so when you take creams, when is it going to spread properly? So this can be related with the viscosity. So to confirm the spreading quality of the cream, viscosity can be used as one of the quality control parameter. When you have the suspension, when can we control the sedimentation? So that sedimentation is linked with the viscosity. So viscosity can be used as one of the quality control parameter. So either it is the spreadability, or it is the stability, or it is the porability. All these terms are related with the viscosity of the dosage form. So by measuring the viscosity of the dosage form, we can confirm its quality to spread, its quality to get poured, its quality to be stable. So that is one of the general application of rheology in pharmaceutical dosage forms. Am I clear?
Yes.
So then we can see the next application of rheology in pharmacy. So this is about the stability of dispersions, where we are going to again look back to Stokes' law. So according to Stokes' law, rate of sedimentation, this V is given as the rate of sedimentation, or you can even call it as the velocity of sedimentation, given with 2r squared d1 minus d2 multiplied by g over 9 neta. So here r square indicates the particle size of the particles or the globules present in the dispersion. D1 and D2 indicates the density difference between the media, or the density difference between the dispersed phase and the dispersion medium. G is the acceleration due to gravity. And the last term that is pending in the equation is, what is this, theta?
Constant.
Which constant? What is this neta?
Viscosity.
Viscosity.
Yeah, it is viscosity. I'm
Viscosity.
surprised. Nobody is able to tell me that it is viscosity.
Viscosity, neta is viscosity.
Exactly. So it is in inverse proportion to the sedimentation factor of the suspension. So it is in inverse proportion to the sedimentation, indicating it is directly proportional to the stability. So when viscosity is more, stability is more. When viscosity is less, stability is less. Because lesser viscosity is going to cause the sedimentation of the particles. When we have the liquid in which the particles are dispersed, if there is more viscosity of this liquid, particles are facing the resistance force to fall down, so that they don't fall, and there will be always maintenance of the uniform dispersion. So this is going to confirm more stability of the dispersion. So thus viscosity is directly related with the stability of the dispersion. Am I clear about the Stokes law?
Yes.
Excuse me, Prof.
Yes.
The last time you gave us this Stokes law formula, I don't know if I had written wrongly, because the viscosity you had written 18 meter. And
Was
today
it
you've
written
written,
18 meter?
that is what I have. I don't know if I am wrong.
Okay. So generally, Stokes law can be written in two ways. The first one is 2r square d1 minus d2 multiplied by g over 9 meter. The fundamental that I generally use is whenever we write radius, then we write the small number 9. The same can be converted into diameter. So 2r square, I'm converting into its diameter because 2r indicates the diameter. So when we write it in terms of diameter, it is 18 meter. So you can see here, instead of 2d, I can write 2r, right? D square indicates
Okay.
2r square. So 2r square is nothing but when you square 2, it is 4, and r square is r square. And it is 2 and it is 9. So whenever we write radius, the bottom term is 9. Whenever we write diameter, because diameter is the bigger one, the bottom term will be 18. Am I clear now?
Yes.
So there should not be any doubt about the Stokes law, whether it is 18 meter or 9 meter. It is the simple thing. Whenever we are writing diameter, it is in terms of 9. And whenever we are writing radius, the bottom will be 9. And whenever we are writing D diameter, the bottom will be 18. Am I clear?
Yes, Prof.
Done. So can we go ahead with the application part? The next one is the artificial tears. How viscosity can be used in artificial tear formulation. Artificial tears are the formulations which are used for dry eye syndrome. So in dry eye syndrome, lacrimal fluid is not secreted. Eye becomes dry. and which will cause irritation during blinking process. Because tear fluid is going to act as the lubricant for the blinking process of the eyelids. So to serve this function, we are going to prepare the artificial tears. So when we go for the preparation of the artificial tears, which polymer do we pick? Do I take cellulose? Do I take dextran? Do I take the normal natural gums? Do I take alginate? So that is dependent on rheology. So now what is the relation of rheology with the tears? So let us consider two different conditions of eye. The first one is non-blinking condition where the eyelid is open. There is no force acting on the eye. So the shear stress during non-blinking condition is zero. The second situation where eyelids started blinking. So we have blinking of the eyelids. So this blinking of the eyelids is going to act as the shearing stress. So there is some force that is acting on the eyelid. So when shear stress is zero, when there is no amount of shear acting, we are representing the non-blinking condition. And during the blinking condition, because of the movement of the eyelids, there is some shear stress acting on the fluid present inside the eye. So what we expect, or generally what tear fluid do is, during non-blinking condition, it remains inside the eye cavity. It doesn't flow down. To remain inside the ophthalmic cavity and to prevent the flowing out, we expect the viscosity of the fluid, which is slightly more. During blinking condition, if still the viscosity remains the same, so that increased viscosity acts as a resistance force. It doesn't allow eyelids to blink easily because there is some thick fluid inside the eye cavity, which is not allowing the eyelids to move. So what happens the moment we start blinking, because of the shear stress that is acting on the tear fluid, they start decrease in viscosity. So this decrease in viscosity facilitates easy blinking of the eyelids. So during non-blinking condition where there is no force acting on the tear fluid remains viscous. The purpose of remaining viscous is it should not flow out or it should not flush out of the ophthalmic cavity, so that it retains its viscosity and it just stays inside the ophthalmic cavity. When it comes to the blinking state, where blinking of the eyelid is creating some shear stress on the tear fluid, if the viscosity is still more, then eyelids will feel that strain to blink. So tear fluid will start to decrease in its viscosity the moment blinking starts. Which type of system is this? Is it a Newtonian system or non-Newtonian system, tear fluid? Did you understand what is happening during non-blinking and blinking?
Yes.
Now tell me, tear fluid is an example of Newtonian system or non-Newtonian system?
Non-Newtonian.
Non-Newtonian system.
Non-Newtonian.
Okay. Again, we have three types in non-Newtonian: plastic, pseudoplastic, and dilatant. Which type of system is tear fluid? Somebody is turning the papers. Please don't wipe everything the moment you come to the next class, please. You tell me the properties of non-Newtonian systems. What do you mean by plastic system? Can anyone from the whole class?
Pseudoplastic flow. Pseudoplastic.
Okay. Can you explain how? Yes, to
The
a
viscosity
tier
of
2.
the viscosity of tears changes depending on the force or the stress applied on it.
Okay. So what is happening to the viscosity the moment we increase shear stress?
It decreases.
Yeah. What do you mean by shear thinning system or pseudoplastic system? What do you mean by shear
System
thinning system?
that it's a system that upon application of shear stress or force on it, the viscosity decreases and it gets more fluid.
Yeah, exactly. So that is the natural rheological behavior of the tear fluids. So when we consider non-blinking condition where there is no action of shear stress, the viscosity is more. The moment eyelids start blinking, shear stress is acting on the fluid and there is a drop in viscosity. The natural rheological behavior of tear fluid is to have the pseudoplastic behavior. So pseudoplastic systems are also called as shear thinning systems because they start thinning the moment we apply shear onto the system. So whenever we are going for the formulation of artificial fluids or the tear fluids, we need to consider the rheological behavior of the polymers that we are going to use for the preparation. So can I select water to prepare the tear fluid? Can I select water to prepare the tear fluid? Why?
Because it has waterfalls and Newtonian system.
Yes, water falls under Newtonian system and there is no change in viscosity. Either it is the blinking condition or non-blinking condition, viscosity of water is going to remain the same. And it won't be able to maintain retention in the eye while non-blinking and getting fluidized while blinking. It won't be able to maintain these two conditions. That's the reason you cannot use Newtonian systems to prepare artificial tears. So the best systems to prepare artificial tears is the pseudoplastic systems. And what are the examples for the pseudoplastic systems?
Gum solution.
What is that?
Gum solution.
Polymeric solutions.
Yes.
Polymeric solutions are the examples for the pseudoplastic systems. So what happens in pseudoplastic systems is you can have the examples of different polymers, like they have, before preparing the artificial tears, they have checked the different polymers, like they have checked the dextran. They have also gone for the checking of the hyaluronic acid. And they have also gone for the checking of the alginate. The moment they have seen the rheological behavior of all these polymers, all of them are pseudoplastic system. All of them will have decrease in viscosity the moment some force is acting on the system. And also they have gone for the use of polyvinyl alcohol. But the moment they have understood how the rheological behavior is changing. Like the moment you go for the application of the shear, what is the decrease in viscosity when they have understood that the moment we apply shear onto hyaluronic acid, there is almost 1,000 times decrease in the viscosity. The moment we apply shear onto the polyvinyl alcohol, there is 2 times decrease in the viscosity. So the moment we apply the same shear onto the dextrol, there is almost a 5 times decrease in viscosity. Alginate, there is 1 to 1.5 times decrease in the viscosity. So when you compare these things, the maximum decrease in viscosity is C in hyaluronic acid with minimum amount of shear. So which is the best shear pseudo plastic system or shear thinning system here? Are you able to understand what I'm explaining?
Yes.
So let me explain again by taking another plain slide. We are looking at the application of rheology in preparing artificial tears. So before going for the preparation of artificial tears, we need to know the natural rheological behavior of artificial tears. So artificial tears are going to behave as shear thinning systems. By nature, they are shear thinning system. Body prepared tears to have thinning the moment we apply shear. The reason is during the non-blinking condition, when eyelids are open, the amount of force acting on the system is 0. So the viscosity of tears is high. The moment eyelids start blinking, shear force acting on the system is increasing and tear fluid will start decrease in viscosity. This increased viscosity helps retaining of the tear fluid inside the ophthalmic cavity. Upon shear during blinking condition, the decrease in viscosity helps in easy blinking and proper lubrication for the movement of eyelids. So this is the natural mechanism how tear fluid is going to act as a shear thinning system. During non-blinking condition at 0 shear stress, viscosity is more. The moment eyelids start blinking as shear stress is acting on the system, the viscosity drops. This drop in viscosity facilitates easy blinking of the eyelids. So when we want to prepare the artificial tears as a pharmaceutical dosage form, we need to look into the rheological behavior of the available polymers. Because we cannot go for the use of Newtonian system, or we cannot go for the use of plastic system. We cannot even go for the use of the dilatant system. The only system that is suitable for the preparation of artificial tears is the pseudoplastic system or shear thinning system. The examples for the shear thinning systems are polymeric solutions. So now when preparing the artificial tears, we are just looking at the rheological behavior of different polymers. Dextrons, polyvinyl alcohol, hyaluronic acid, and alginate. So just a comparative basis. So which of them is going to have proper pseudo thinning so that they will be suitable to prepare the artificial tears. So when they have checked the shear thinning properties of these polymers, so they have seen almost 5 times decrease in viscosity, and they have seen around 1.5 times viscosity drop in polyvinyl alcohol, 1.5 to 2, and whereas in hyaluronic acid, almost there is 1,000 times decrease in viscosity. When we prepare 1% solution, the viscosity might be around 50 centipoise or maybe around 100 centipoise. So the moment shear is applied onto this system, this viscosity decreased by 1000 times. Now the viscosity is 0.01 CPS. So that is the difference in the viscosity, or that is the drop in viscosity that hyaluronic acid is able to show. And when it is the case with alginate, it is also again showing the same viscosity drop like 1 to 2 times. So when you look at these polymers of dextran, polyvinyl alcohol, and alginate, there is a small drop in viscosity. But the moment you see, just with the preparation of small concentrations of polymeric solution, there is a heavy drop in viscosity which is required to mimic the action of artificial tears. So that's the reason hyaluronic acid is a very, very popular polymer in order to mimic the body fluids. It can be used in the preparation of artificial tears. It can be used in the preparation of synovial fluid. It can be used in the preparation of wherever lubrication is required, like during the condition of arthritis, in case of knee pain, where the fluid which is lubricating the movement of the joints is completely dried up. Now the bones will start getting friction between each other and they start inflammation. So this inflammation is the main reason for the pain in the knees. So there, the fluid is injected, the artificial fluid which can mimic the lubricant present in the joints. So they go for injection with the hyaluronic acid because it is having the capacity to lubricate. When it is in stationary condition without any joint movement, the fluid will be thick so that it will just remain inside the cavity, the bone cavity. The moment joints will start moving, it is the shear which is acting on the fluid. It will start getting thin. There will be a drop in viscosity, and that will be facilitating easy movement of the bones. So that is the application of rheology in the preparation of artificial tears or in the preparation of artificial lubricants required for the body mechanisms. Am I clear?
Clear.
Yes.
Any doubts, any questions? Sure? Okay. So now polymeric solutions. Polymeric solutions are used in various fields in pharmacy. So we have various polymers. Just now we have seen 4 different examples of the polymers. Now again, we have the examples of the binders used during the tablet granulation. And also we have the examples of the polaxomers. We have the examples of natural gums, cellulose derivatives, all these things. So when we want to use them in particular situation, or maybe we are using a gum solution to prepare the binding. So what is the viscosity that it is going to have? And while mixing, when we are applying the shear, what is the drop in viscosity that it is going to bring? So all these things are very, very important. So that is the reason understanding the rheological behavior of polymeric solutions plays very, very important role in pharmaceutical applications. Either it is the sol-gel behavior. Sol-gel behavior indicates you initially the viscosity is less and during shear, viscosity is more. Our gel to sol behavior, sol indicates a thinner liquid. Gel indicates a thicker liquid. So gel is with increased viscosity, and when it is getting into sol state, there is a decrease in viscosity. Shear thickening systems are called as sol gel systems. And gel to sol are shear thinning system. Generally, polymeric solutions, they will have gel to sol formation. And what is the drop in viscosity that they are showing? So whether this drop in viscosity is going to influence the process or not, whether this drop in viscosity is going to influence the stability or not. So we need to be very, very careful about all these things. So take the example of acacia. Acacia gum or tragacanth gum, these are the general ingredients that are used in the preparation of emulsion. Did you prepare emulsion by using acacia gum and tragacanth gum when you are in your third year, 3.1?
Yes.
So we are using this as an emulsifying agent. So what is the purpose of an emulsifying agent? It emulsifies oil globules or liquid. If water is emulsified, then it is emulsified into oil. Or if what oil is emulsified, it is emulsified into water. Acacia and tragacanth, again, they come under the category of polymers. Now, what is the behavior of polymers in regard to rheology? What is the behavior of polymers in regard to rheology?
Shear thinning.
Pseudoplastic flow.
Yeah, pseudoplastic or shear thinning. So they get from gel to solid. There will be a drop in viscosity the moment we apply force onto the system. So now we prepare the emulsion. Emulsion is ready by using acacia and a tragacanth. Now when this emulsion is shaken before using, we are applying shear. So what happens to the viscosity of the system when we apply shear?
Decreases.
Viscosity is decreasing. So is it stable now or not? So that is dependent on what is the viscosity drop when this particular amount of force is applied. Now you see, you have seen the example of hyaluronic acid. With the simple application of the force, there is 1,000 times decrease in the viscosity. If even acacia and tragacanth are going to show you the same similar type of behavior, then there will be a problem with the stability of the emulsion. So now, among the available polymers that we are using in pharmacy for different purposes, we need to have an idea about the rheological behavior. So hyaluronic acid with maximum drop in viscosity, it can be used to mimic the body fluids. But you cannot expect the same rheological behavior when you are using a polymer for the emulsification purpose. In this particular situation, when acacia and tragacanth are used as emulsifying agent, and with a simple shaking, there is a drop in viscosity by 1,000 times. Now the emulsion is becoming very fluid-like. All the droplets will separate because viscosity is in proportion with stability in dispersions. When viscosity decreases, stability decreases. When viscosity increases, stability increases. So when there is a drop in viscosity, automatically the stability of the emulsion is going to decrease. So we need to be careful about what is the application of the polymer, whether that rheological behavior of that particular polymer is useful in that application or not. So then only we will be able to achieve the required function of the polymer in the selected dosage form. Am I clear?
Yes.
Clear.
Yes.
Then the thixotropic applications, just to revise, what do you mean by thixotropy? We can see when the plastic system is starting with a curve and a straight line, it is going up in this direction. The moment we stop shearing, it is coming back by slightly moving to left. So which is indicating there is a drop in viscosity, which is called as thixotropy. So the same drop in viscosity is indicated for the pseudoplastic system in the other graph. So what is the application of thixotropy in pharmacy is the moment we shake suspensions or emulsions, the thixotropy must be less. If the polymer selected or the suspending agent selected or emulsifying agent selected is showing the maximum thixotropy. Maximum thixotropy indicates you maximum drop in viscosity. The moment you stop shaking and keeping it back to the shelf, there should not be maximum thixotropy. We need to be very, very careful about the thixotropic behavior of the pseudoplastic systems, because thixotropy is related with the drop in viscosity, and this drop in viscosity is shown by pseudoplastic systems. So again, related with the polymers. So whatever the polymers that are showing the maximum thixotropy are not suitable for preparing dispersions. They are not suitable for preparing solid structures like lipsticks and deodorant sticks. The same thing happens when deodorant or lipstick is rubbed against the skin. There will be drop in viscosity because the polymers that we are going to use are the pseudoplastic. But the moment you are removing the rubbing, so the polymer should regain its viscosity and it again get back into its original solid structure. So we need to be careful in selecting the polymers for this type of formulations so that they will not give you any stability problems. If thixotropy is maximum, definitely will end up with stability problems like sedimentation and problems like damage of the structure or damage of the appearance in case of lipsticks and deodorant sticks in pharmacy. So that is the application of thixotropy in pharmacy. Am I clear?
Clear.
Yes.
The next one, application of rheology in tablet granulation. This is with respect to the wet granulation process. We don't have rheological applications in dry granulation because we don't add any liquid in dry granulation. The powder is directly used for the slugging process and it is kept for compression. Whereas in wet granulation, we go for the addition of liquid binder. So when we add liquid binder, the powder enters into different stages. So whatever the diagrams that you have seen in the picture, so these are all the different stages. Are you able to see those diagrams? The first stage is called as pendular stage. The moment we start adding liquid binder, you can see the small bridge-like structures.
No, Prof, we can't see the diagram.
Are you able to see my slides when I'm explaining?
Yes.
Yes, we can be able to see
Up to thixotropic applications.
application.
Then what happened with this one?
I think it was frozen.
Yes, there
Are
you are.
Yeah, you are able to see now, right?
Yes.
Yeah. So there are 4 different stages for the granulation when we go for the addition of liquid binder. The moment we start adding the liquid binder, the powder enters into the pendular stage. The first stage is called as pendular stage. Whatever the liquid that we are adding to the particles, now we'll have formation of small bridges or thin bridges between the particles. Can you see those thin blue color bridges which I am highlighting with red now?
Yes.
Yes, we can see.
Yeah. When the liquid forms as a thin film between the particles, then that stage is called as pendular. Now the mass is not ready for the granulation. So we go for the addition of further amount of the liquid binder. Now you can see the second stage, which is called as funicular stage. So when it is the funicular stage, now the liquid bridge is thickening. You can see the formation of thick bridges of liquid between the particles. Can you see those bridges?
Yes, we can see the bridges.
Yeah, this stage is called as funicular stage. And after this, when we go for still further addition of the liquid binder, now the liquid binder gets filled in between the particles. And it enters into a stage called as capillary stage. So whatever the gaps present between the particle, now everything filled by the liquid binder that we have added. And if you further go for the addition of liquid binder, then that will enter into a droplet stage. The final stage of granulation is called as droplet stage. So at droplet stage, the particles will start floating in the liquid binder. We have added more amount of liquid binder, and now the particle from a wet mass stage has entered into a fluidized state. Now particles are floating inside the liquid binder. So this is what happens the moment we go for the addition of liquid binder to the powder mass. Initially, the amount of liquid that we added will form thin film-like structure between the particles. That is called as pendular stage. And the next addition will thicken the film, and the stage is called as funicular stage. And when we further add the liquid gets filled in between the particles, resulting in a capillary stage. Further addition of the liquid makes the particles to float inside the liquid, and the stage is called as a droplet stage. Now, what is the relation of this liquid addition to the rheology, and what is the relation of this liquid addition to the proper granulation? That can be explained by using this graph. Can you see the graph?
No.
No.
Just wait, it will come.
Not yet, not yet.
Confirm once you see the graph.
Yes.
Yeah.
No.
So you can't see or you can see?
You
You
can
can
see.
see.
So on the x-axis, it is the amount of binder that we have added, or it is represented as L to S ratio, liquid to solid ratio, which is given as number of ml that we have added with the weight of the solid. Or otherwise, you can simply mention it as the amount of binder that we have added. And on y-axis, we are using torque. Torque indicates the force required to start any one function. So in this situation, the force required for punching of the tablet. So as we start adding the amount of binder, the torque is increasing. So it is slowly increasing, and then it is reaching a maximum, and then it is falling down again. You can see that. So these are the stages. The peak torque is presented at capillary stage. The moment we add more amount of liquid binder than capillary state, the force that is required is decreasing. The amount of force received by the tablet granules to get compressed is falling down. Whereas when you start, they enter into the pendular stage, then they enter into the funicular stage, and then they enter into the capillary stage. So slowly the force that is transmitted is increasing. It is reaching a peak, and then once the granules are crossing the capillary stage, you can see here in the previous slide. So pendular, it is increasing. Yes, the force is transmitted to the granules, and even at funicular, it is increasing. It is reaching a maximum at capillary. It is showing maximum at capillary. Once the capillary stage is crossed, now the force is not utilized for the compression because the rheological properties are influencing the punching. It has become more fluid-like. You cannot punch that wet mass. So we need to always stop at capillary stage. So that is the reason we slowly go for the addition of liquid binder even when we are preparing chapati dough. So we just add liquid binder so that all the particles are bound together. We don't add a liquid where particles will start floating. We just add liquid which is sufficient to bind the particles together. Once the particles are bound together, then that is the stage where the viscosity is proper and you can punch them in the form of the tablet. So that ability to punch, get them punched into tablet form is measured by using the term called as TAR. So that is the application of rheological properties in tablet granulation. Am I clear about the stages in tablet granulation and about the torque that is used in the tablet punching?
Yes.
Yes, Prof.
So that is about
Yes.
the application of rheology in pharmacy. And also we have seen some general applications of rheology when we started our class, like it is useful in absorption, like when the liquid consistency or the fluid consistency inside the GIT is less, then you can expect more amount of absorption. And even same thing, when the liquid consistency is less, you can expect more amount of drug to be dissolved. So these two are directly related with the bioavailability of the drug. Viscosity of GIT fluids influences the bioavailability. When viscosity is more, dissolution is less, absorption is less, so bioavailability is less. So that is another general application of rheology. Any doubts in today's class? You can take
I have
5
a
minutes
question.
time to go through whatever we have discussed. And if you have any doubts or any repetitions to be done, you can ask me. I'll go for a repetition.
Oh, could I please ask a question?
Yes, I can hear somebody asking something.
Yes, I don't know. This will be taking you back a little bit. There's something which was not clear to me. Yes.
Yeah.
Concerning the Stokes law.
Okay.
I heard you explaining it, but it didn't come out clearly to me. So I beg for a clarification on the same. Based on Formula One, and I'm seeing two formulas here, which is a bit confusing. You explain it, I know, but yes.
I will do it again.
Thank you.
So Stokes' law says V is equal to 2R square D1 minus D2 multiplied by G over 9 neta. This is Stokes' law. The same Stokes' law can also be written in terms of diameter. So this is small r indicating the radius of the particle. So this is the capital D indicating the diameter of the particle. When you represent it in terms of diameter, it is D1. So this small d1 and small d2 are for densities for the dispersed phase and the dispersion medium. So now we are going to use 18 in denominator. Why are we using 18 in denominator is, like you see this one, D is 2R. Do you agree?
Yes.
Can we write diameter as 2 multiplied by radius?
Yes.
Yeah. So I'm using the 2R in the place of diameter. I'm using the square. So now rest of the things I'm not changing. D1 minus D2 multiplied by G over 18 neta. I'm not changing anything. Only in place of capital D, I used 2R. So now when you expand this, 2R whole square is nothing but 2 square and R square, which is 4R square. Do you agree? Do you agree or not?
Yes, I agree.
So I'm writing this 4R square in the equation. Only this one I converted to 4R square. Rest of the thing remains same. D1 minus D2 multiplied by G over 18 neta. 2, 9, which is nothing but 2R square D1 minus D2 multiplied by G over 9 neta. It is simple that Stokes' law, is it expressed in terms of radius or is it expressed in terms of diameter? Because particle size can be measured both by radius and diameter. When you use radius, because radius is, this is my hint. Radius is a small term, we use 9. When we use diameter, diameter is a big term, we use 18 in the denominator. Am I clear now?
Yes,
Yeah.
you are clear. Now,
Is
in
it
case
okay?
we, just a minute again, in case we are asked to explain the parameters within the Stokes law, we do it in reference to either or both or one of them.
you refer it to particle size. Because both radius and diameter, they represent particle size. You either mention in terms of radius or you mention it in terms of diameter, it is okay. Sorry, there is an interruption by internet. Am I audible now?
Yes, you are.
Yes, you are.
Yes, Prof.
Yes. Is
Prof,
it
I
the
have a
question
question.
only about the formula or any other questions?
I have another question.
Yeah, please.
We go back to the hyaluronic acid,
Okay.
assuming because of its properties and its non-Newtonian nature, it is ideal, an ideal solution to replace tears. But now, in some cases, you also have dextran, and it seems like dextran does not have a good elastic memory at rest. So I'm bothered to question why do we also use dextran in ophthalmic preparations? And in some cases, we use it also for, I think, for parental preparations.
Can you hear me now?
We can hear you partly.
Okay, somebody was asking me about the hyaluronic acid.
Yes, that's the comparison of, because I think hyaluronic acid in its application in ophthalmology, and because of its properties, it is probably the best choice when you are trying to work with artificial tears. But in some cases, we have preparations that contain dextran. And my assumption is that dextran does not have a good elastic memory, and it's still being used.
Whatever the polymers that I have mentioned, all of them are useful in preparing the artificial tears. All of them. Either it is the PVA or it is the alginate or the hyaluronic acid and dextran. Actually, if you could remember, I have also projected one diagram, one graph. So how viscosity is changing in artificial tears. I have mentioned around 10 to 15 brands of the artificial tears containing different polymers and how the viscosity is dropping in them. So the slope, or how the slope is decreasing there, how the curve is falling down there with the increase in the shear. So when you compare these four polymers which are useful for the preparation of artificial tears, Among them, hyaluronic acid is the best one because of its excellent shear thinning property. So just to have a comparison how thinning happens with the different polymers, I have taken that example.
Yes.
Am I clear?
That's good. Clear, Prof.
Any other questions by any other student? Questions are welcome. More questions, more information.
For me, I'm requesting you repeat on the aspect of granulation, tablet granulations as an application for rheological properties.
Now I won't be able to project the slide because of this technical issue, but I can explain it orally. So generally wet granulation is done by adding a liquid binder to the powder mass. We add liquid binder slowly until a wet mass is prepared. And then this wet mass is transferred to the sieve, granules are formed, and then we go for the drying and compression. So now the experiment is conducted to know how the rheological behavior of the added binder is influencing the compression force. They have considered the compression force in terms of torque. Generally, torque is called as the minimum amount of force required for the commencement of the work, or just to start the work, what is the amount of force that we require. So that is called as the torque. So now when we go for the addition of liquid binder to the powder mass, there are 4 different stages that are going to happen. So in initial stage, when we add little amount of binder, so that binder is going to form as a thin bridge between the particles. And this stage is called as pendular stage. When you go for further addition of the liquid binder, now that thin bridge will become broadened. So now you'll have the formation of thick bridges between the particles, and the stage is called as funicular stage. If further liquid binder is added, now the particles will start getting bound to each other with the liquid getting filled between the particle, and this stage is called as capillary stage. And further addition of liquid will make more amount of liquid in the powder mass. So at that stage, the particles now will start floating inside the added liquid binder. So when the compression is done by taking all of these stages of granulation, it was identified that slowly the force that is transmitted increases. Maximum amount of force is transmitted for compression at capillary stage. And then again, there is a decline in the amount of force transmitted. So it indicates because of the rheological properties where when we go for the addition of little amount of binder, the binder was scanty and it is not flowing. The next stage also, it was scanty, it is not flowing. In capillary, it has reached the maximum. It can get filled between the particles. It has reached the maximum, after which it completely flows. Now the fluidity is increasing. It has reached the maximum amount of tightness with the capillary stage. If you add a little more binder after that, the fluidity is increasing. Now from the tightness, it is becoming very loose structure. So that is the reason the torque is increasing until the capillary stage. And after that, there is a decline in the amount of force transmitted for the compression. Am I clear now?
Yes.
Yes, clear.
Any other questions? Thank you. Any other questions? About thixotropy, negative thixotropy, rheoplexy. So with this, we are done with the rheology. This Thursday, I'm going to start with the interfacial phenomena. which will take 2 classes. So this week and next week will be done with the interfacial phenomena. I would like to have one more online class. Once we are done with interfacial phenomena, am I clear?
Clear,
See,
Prof.
interfacial phenomena, I don't want to take through online because it involves a lot of equations. I want to do it during physical class so that I can see whether you are able to understand those equations or not. Once we are done with interfacial phenomena, we'll see about complexation, which doesn't have even a single equation. Complexation we can see through online, and then colloidal dispersion and phase equilibrium we can do via physical classes. Are we clear?
Clear, Prof.
Yes, Prof.
Okay. One more chance to ask me any questions.
Very clear.
Okay. Then can we close the class?
Yes, we can close the class.
Not
Thank you. Thank you. Have a nice evening. Thank you very much. I appreciate your efforts.
Nice.
Thank you so much, Prof.
Welcome.
We appreciate.
Thank you.